Hello. All right. Yeah, we're the Evaders, and this talk will be about the recent jailbreak we did called Evasion. It's going to be a pretty complex jailbreak, and we have an hour, so try to get through this as quickly as possible. Um, First off, we want to go over how the justification for all the complexity that we're doing right now. Um, the eventual goal is to execute a kernel exploit, but there's a lot of steps to getting to execute the kernel exploit. One of the first requirements is to run unsigned code outside the sandbox. One of the other requirements is to get around the ASLR that is in the userland and also in the kernel. And then finally, we need to, of course, take control of the kernel. So in order to run unsigned code, we can actually divide the requirements for running unsigned code into 3 different sub-requirements. The first one is that we need to write to the root file system, specifically a file called Evad3rs.launchd.conf. The second requirement is that we need to disable code signing somehow. And then the third requirement is that we need to convince launch control to run a program as root. And yeah, these slides are kind of weird. Okay, so in iOS 6.1, launch control had some security upgrades to it. Instead of being loaded from the file system, launch daemons, which are a set of system daemons that are loaded on the startup of iOS that we can typically use to use in an untethered exploit to trigger some execution at boot. It used to be that these daemons are configured from the file system. There's a series of configuration files on the file system. But now they're not loaded directly from the file system, but they're loaded from a signed cache. These daemons are now signed. And the launch daemon configuration files on the file system are ignored. However, this hardening still, in this hardening, the launchd.conf file, configuration file, is still available. And we've been using this file to be the linchpin of our untethered jailbreak since, at least since the Corona untethered jailbreak. And one of the abilities of this configuration file, is, if you're able to write to it, is that you can execute any command that launchd can execute. And launchd is basically the first process that gets executed in iOS. It's basically the initd of iOS and Mac OS X. So with the exception of loading file system launch daemons, which are now signed, we can do anything with launchd as long as we're able to write this configuration file. One of the commands that we can use with launchd is called bsexec. And bsexec, we can run arbitrary programs on the arbitrary programs at boot, as long as we have a way to get around code signing. So, right. So now we basically need to be able to figure out how to write to a root file system so that we can write write this configuration file. And we also need to and as long as we can write this configuration file, the third requirement is also fulfilled. And also then we just need to figure out how to disable code signing. So now Nikias will talk about how we're going to write to the root file system in order to write that configuration file. So.
Okay, hi everyone. So I'm going to present how we managed to actually remount the root file system and how we prepare the device for the untether. So for the injection, we actually have 3 steps. The first is, as already mentioned, to remount the root file system. Then we have to write this configuration file, the etc launchd.conf, and we have to transfer the evasion untether payload that will be used for the initial code execution on boot up. So, what's happening? Okay, so during our research, we found out that we can use the launchddl command to make launchd run commands, and this works by a control socket that's created by launchd. So if execute the launchctl command, it will talk to the socket and thus talk to launchd. But the problem is that the socket file only is accessible by root. So as user mobile, you cannot run the command. You can run the command, but it will not have any effect. It will just fail. So to remount the root file system, we have to actually do two things. We need to find a way to execute the launchctl command, and we have to change the socket permissions, because we're not root. So there's a way to execute a command. If we replace the binary of an existing app with a shell script with a specific shebang line, we can execute an arbitrary command. But since we don't want to mess up any existing app, we would either have to add a new app or just use one of the pre-installed hidden apps that are present on device. And for our purpose, we misuse the demo app. So if we want to add an app or an icon, we have to modify a specific file. It's the COM Apple Mobile Installation plist file. That file holds a state of all apps that are on the device, that are App Store apps and also system apps. And it is not accessible using the AFC protocol, and it's not included in the backup. So we actually need to find a way to grab this file. But luckily, the file relay service is possible to transfer this file to the computer. Now that we have this file, we need to modify it to our benefit. So we actually have to first change the path of the demo app, the demo app to point to our fake app location. And to make it actually show up, because it's by default hidden, we have to remove some keys in this plist file. This is the SB app tags key. And for some reason, the iPad has an additional check for this specific type of apps. So we have to remove the application type key. Otherwise, the icon would never show up. Okay, so now we know what we have to change. And we have to add an environment variable, because if we execute the launchctl command, it will not know the location of the launchd socket unless we set an environment variable that's a launchd socket variable pointing to the actual socket file. Okay, so now that we know what we have to change, we have to write the file back. The problem is that the file relay service is not allowing us to transfer any file at all to the device. So we have to find another way. We need some kind of write anywhere vulnerability to actually being able to write this file back. What we have here is a directory traversal that we found in the mobile backup service. Okay, some words about mobile backup too. It has a set of predefined backup domains that specify paths that are allowed for restore, actually for backup and restore, and it's very specific. Some of the paths just allow specific file names, and so we cannot just use any location to add a specific file. But luckily, there are enough possibilities to still add some files, like the media recordings folder in the media domain that allows basically any file name to be added to the backup. One more thing is that since iOS 6, the backup restore process has changed because the files are, when the restore is in progress, the files will be created in the TMP folder and then staged to another directory in the var file system, and then they are at the end renamed to the final destination. So this obviously limits the way we could create files to the var partition, but because the rename of operations actually prevent us to rename that file to the root file system. It's by design not working. So for the directory traversal, we can use a trick in the way we planned a symlink in one of the allowed paths. We use the media recordings, put a symlink, and this symlink points to the location where we want to create the files we need. So when the backup is restored, instead of actually writing to that backup domain path, we actually write to the path we set with the symlink. So, and using this technique, we are able to write the files we need. We can write the installation plist file, and we can write the files we need for our fake app. So The only thing we have to do right now remaining is that we reboot the device, and then we will actually get the icon show up. Okay, so we just saw on the previous slide that we uploaded the demo app file, and this one is actually not a binary program, it is a script, as mentioned before, sorry. And this script is containing a specific shebang line and to remount to execute the mount command, so we can remount the root file system. But as you can see, there's no mount point included in the command line, so it's actually not, the command would not know where to mount. Well, it will know because of the nature of shebang, the path of the app will be added to the command line. So what actually happens is that the mount command will try to mount the root file system to the app binary, which of course doesn't work because it's not a folder. So this initially fails. To resolve this, we use the mobile backup trick again and change the actual script with a symlink pointing to the root file system. And this way we will get the root file system remounted. Well, not quite, because we still have to make sure that we actually are allowed to run this command, because we're still not root. So what's remaining now is that we have to change the socket permissions for the launch control socket. First question is, why don't we use the mobile backup directory traversal? Because the problem is that when we restore something, the files will get created and not, we cannot change the permissions of existing files. And the second thing is we cannot create socket files. So even if we could create them, it wouldn't work because we would have to use the existing one and not create another one because it would not be able to talk to launchd. So to achieve this, we still need to use the mobile backup system to plant the file. So initially we actually thought we could use that to change the permissions, but then we found out that we cannot use that and we needed a solution. And I was searching for some chmod command and found out that lockdown is doing this, and I was looking through the disassembly and found this small piece of code actually showing that we have here a hard-coded chmod to world readable, writable, and executable, and this is not checked any further, so it's because it's a hard-coded path, and it's executed every launch. It's a sub-function of the main function, so every time lockdown D is started, it will execute this chmod command. So this is just perfect for our goal, and so we use the mobile backup directory traversal again to add a symlink. That's VARDB time zone, and this one points to what we want to change. In this case, it's first the var_tmp launchd folder, and then the var_tmp launchd socket file. So, but we still need to make launchd restart, but this is not hard. We just send some malformed property list, and it will crash. And because launchd is restarting lockdown D immediately, it will just execute this chmod. So now we are good, and we have changed the socket permissions, and the actual launchd command will succeed and remount the root file system. Okay, so next step is to write etc launchd file. The problem is that this file sits on the root file system, and we could try to use a mobile backup system, but the problem is because of the mobile backup system is actually does not allow to create files outside the var partition. We still need to find a way to do this, but it's not so hard because unlike regular files, a mobile backup system is actually creating the symlinks directly in the staging directory instead of like files creating them in TMP and rename them and moving to the staging directory and then renaming them to the destination. So we are lucky and we can send this symlink, which will then point to, the name of the symlink is etc launchd_conf, and this points to our own version of the launchd_conf. So Because launchd is not checking if it's a symlink or something, it will still just load that file that actually is a symlink pointing to our file. And so we're actually good. We write the file, and launchd will be able to use it. So the only thing remaining right now is that we have to upload the untether payload, which is not very hard. We could have used AFC, but since we already have the mobile backup directory traversal, we just use that one again to upload the files we need for the untether. And additionally, we upload the Cydia package and package list using the AFC protocol. Okay. Yeah, that's basically it. So we have remounted the root file system, we wrote the etc launchd-conf, and we uploaded the untether payload, and now we're ready to reboot to untether.
Thank you, Nikias. Okay, so Nikias explains to us how he managed to be able to put the untether to the file system. It was, as you have seen, a really complicated problem because he had to pass through a lot of stuff, a lot of exploits and vulnerabilities. So yeah, it was a good job. Now, there's still the second point that you've seen at the early part of the presentation. We still need to disable code signing in a way. So, about code signing, where are the protections? Where is it verified? Where is it enforced? First, when the kernel load binaries. When some process try to access executable pages, the kernel will verify at that time that everything's correct. And of course, when you try to access signed pages, even if they are not executable, kernel will verify that everything's good, that they are not tainted, and stuff like that. So, how is enforced security for signed page access? It's enforced in a kernel method that is called VM fault enter. And this method, basically, to be able to verify and kill your process if something bad happened, it depends on CS blobs to be registered somehow. The blobs will indicate range of the file that is signed and the corresponding hashes. If there are no blobs loaded, then no checking is done. We believe this is because of OS X and iOS compatibility. OS X doesn't require code signing. It can use code signing with this with new gatekeeper stuff, but it does not require it totally. So now, where our executable pages are verified, it's again enforced in VM fault enter. And if a process tries to access an executable page that is not signed, it is killed. But yeah, it is killed depending on some property on the process that is CS kill. And this property is added for every single binary on iOS because of some hook of a specific kernel extension, which is AMFI. So, how code is loaded? I mean, code is either binary code or library code. So, the code can be loaded through two passes. Executables are loaded by the kernel, and libraries are loaded by DLD. And each pass has to validate that the code is signed separately in its own way. So, how does it work loading a binary? The kernel gets an execution syscall and some mandatory access control hook is played there by the AMFI specific iOS kernel extension. And this will trigger some method call of it, which is MPO vnode check exec. And this special method will set the CS hard and CS kill properties on the process, like I said earlier. This does not happen on OS 6, of course. OS 10, sorry. The kernel then loads CS blobs from the binary, the macro file, and some hook again in the tree of that execution method is called. This MPO vnode check signature will call a user learned daemon that is called AMFID to do the validation. Yeah, this is kind of weird. You'll see that. And if signature checking fails, the kernel will kill the process. Then the other pass, how loading a dilib is done. Basically, the blobs of the dilib needs to be uploaded to, uploaded is not the right word, but where you see the idea, uploaded to the kernel somehow. So dyld, the library loader, will call some syscall to add these blobs to the kernel. Here are the here's some code showing you that when load code, if the library is signed, then it will call some method that is load code signature. And this method in dyld will call the particular fnctl syscall to add the blobs. But it does that only, of course, the dilib is signed. So we can kind of sum up the dependencies between all of this. As you can see, this is really complicated, and we simplified this to the maximum so that you can see. Too bad I don't have a laser pointer or anything. Nikias, do you have your laser pointer? Oh, thank you. Perfect. Okay. So let me try to explain this graph in a simple manner. So these are the different dependencies. So to exec VE to do his job, he has to know the signature blobs. If it's a library, the blobs are uploaded by this particular syscall when the process tries to load the library. If you try to execute a binary with exec VE, that will trigger some method in the AMFI, this one, and this method will add this particular dependency for the wall code signing stuff to work. So for the VM fault enter, the one checking the pages to work and to kill your process if there's a problem, it requires to work that this CS kill property is set and that it adds the correct blobs to verify the pages. And everything here, the blobs, come to that particular method in case of a binary in AMFI, which will call a daemon process that's using some kind of dylib to validate the signature. So yeah, it's kind of weird because it's a process that's also using a dylib, and yeah, it's so complicated, as you can see. So now talking about AMFID. So all binaries shipped with iOS, AMFID included, of course. have hashes in the kernel, so that there's no chicken and egg problem. AMFID don't have to verify itself that it is correctly signed. In fact, it's a kernel verifying it. And AMFID, as I said, use some kind of library to verify the code signature on binaries. If it passes, if AMFID says OK, then the kernel will continue to load the binary no matter what. I mean, in a code signing point of view. So what are the weaknesses of this? Blobs are validated outside the kernel in some kind of userland process. Why? We don't really know. Maybe some design architecture Apple choose to do at some time. But it's so complex. Yeah. And as long as AMFID gives the permission, the kernel will accept any blob, even if it's invalid. So the weak part, of course, is the userland process. So our idea here is to convince AMFID in some way to say, your program is good, even if it's not signed. So let's focus some minute on library loading now. So DYLD takes care of loading the dependent libraries in the Mac-O. And also handles dynamic loading with the DL open syscall, not syscall, a function. And DYLD runs in the process, so it has basically all the permissions of the process, no more permission than the process has. And conversely, each process has to be able to do what DYLD can do. So, can we load unsigned dilibs, by the way? There's some kind of protection against this, a weak protection, but some kind of protection. DYLD tries to prevent this by requiring the Mac-O header of dylibs to be executable. That's, it doesn't require that the library is signed. It requires that the library is executable. That sounds weird, but it is the truth. So why? Because they consider that if the library is executable anyway, the kernel will check the page access, so it's OK. So, of course, if you access any unsigned executable pages, that will crash, that will kill the process. Kernel will trigger and kill you. But why just trying to do some interposition and without any code, just data pages? Would that work? No, because there's a requirement. Anyway, load commands, all load commands of the Mac-O header has to be in an executable segment. So, in fact, you can't have no executable segments at all because there is this requirement. And this header has to span the at least the entire Mac-O header file offsets. And there, yeah, of course, must be at least one Dutch segment. But who says that the Mac-O header actually used by DYLD has to be at the front of the file? There's no condition for this. So here we just added another segment which is executable. Oh, it's so small. Here it's executable. It spans the entire Mac-O file header, but we added another segment that is not executable this time. So we won't hit the kernel will kill you problem. And it contains, of course, some interposition stuff. So that's how it works. That's how we bypassed the process of verification. And oh yeah, it works also because mmap on OS X, or OS 10 or iOS, mmap will replace the previous mapping anyway. So this mapping is exactly the same as the previous one. So basically, this one will kind of replace this one anyway. And now, of course, we can do some interposition and we can override some functions. And this is an interesting function in AMFID because this one verifies the blobs and stuff, and you have the error pass saying, oh, it failed, and the OK pass here. And yeah. And this particular call here happens in the libmiss dylib that is required by AMFID to work. So we can interpose that one somehow. Here is the idea. We just replace, we override that call so that it always returns 0 by forwarding it to another random function in the shared cache. So yes, the whole security here with just some clever library injection is a big fail because of the weak point here. The whole dependency between, of the blobs here, the blobs are poisoned somehow and everything is okay. Nobody will kill you. That works. So yeah, we convinced AMFID to okay our program. And we did this without any memory corruption at all, just by injecting some little and simple library. Here is a real-world example of the configuration file that we added at bootup, loading the library, killing the, doing the stuff with AMFI. Here it is. So here come the most interesting parts, the kernel one, and Eric will follow.
Yes, thank you. Can you hear me? Is my mic on? Yes, yes. So that's great. We've got code signing defeated, and we can do a lot of things on the phone at this point that the average phone can't, but we need to go off into the kernel and sort of finish the job to make it more applicable to the types of jailbreak apps that we run. So let's jump into it. The actual binary, it's interesting. If, at the end of the day, if you exclude all of the temporary code that was discarded because they were dead ends, you end up with about 5,000 lines of code. About 1,700 of this, I think all of this will end up on GitHub if it's not already Planet Being, the dynamically finding offset code.
Yeah, what's the base?
So the bulk of the code there is on GitHub or will be soon. The remaining, in descending order of quantity here, you've got code for primitives that are used to sort of step towards the goal, and we'll talk about that. You've got the 318 lines of primitives just for task for PID 0 after it's enabled. So you've got, most of this is gobbledygook, but this first bullet point, 1719, that's useful code and it's public domain and it'll be handy going forward. This is the first jailbreak in a while that we haven't had to have everyone, every model of iPhone or iPad out there and dole out to try to get them to give addresses, offsets based on the model. So this dynamically finding offsets is something that was desperately needed and David coded. It comes down to the core vulnerability that we're using is a USB vulnerability. It's the eternal source of problems for Apple and for a lot of other devices too. Specifically, we're using this I/O USB device interface, which is part of an API for an application to make use of USB on an iOS device, or on a desktop. And it has not just one vulnerability that would have probably been useful by itself, but there was a second one which made it even more useful. And it was only a few methods down. With these two fundamental vulnerabilities, we create a few exploit primitives, and then you take these primitives and you combine them to achieve all the remaining goals. The actual calls, the actual methods that were a problem, this is just a subset. There's 20 or 25 methods in this interface. But the ones that were a problem are stall pipe, which is 15, numbered 15 in that list. And a few down is the create data. Stall pipe lets us, it without doing any serious checking, it just accepts a pointer that's provided to it from the user side, and imbues a lot of importance onto it, and assumes that it's correctly formatted and it's the right kind of object, and you'll see in a second why it's not. And the second one here, the create data, is useful because it's an address leak, basically. It allows us to derive the kernel offset of the slide. This map token that it returns, in general, it can be anything that's unique. All that's required of the actual call is that the token itself is unique. The shortest way to do that is to make it an address. The address doesn't mean anything to the user land application because it's in a different address space anyway, and it can't access it because of that. So it's a quick and dirty way to get something unique, and that's what Apple did. Get big. Now, most of these libraries, there's one side of these libraries where you can get the source on open source on Apple's website. This is not one of them, so we had to reverse engineer the kernel extensions that implemented this. And these are serious. These two vulnerabilities, and in fact, even that first vulnerability alone, is sufficiently powerful to enable everything else that happens. Like I said, we don't have the source code for this part, but these are the three routines that end up. This is your main entry point, and whether or not you pass certain conditions, you'll either call this or go through there. We don't have the source code. David sat down and wrote this very, straightforward translation, I guess, from all these offsets into this code. It's probably not very obvious, but it's best thought of. This is just an if, and this right here is a function, and then this right here are all the arguments to that function. And if you follow all the parentheses, you'll see that sticks out. So you do a little bit massaging of that. It looks a bit more clean. You've gone from bytes to dword, and then when you think of it in terms of a C++ kind of a thing with objects, you sort of derive this much cleaner representation of what the actual function is. And it's important. This is the important version. All these are equivalent, but this is obviously the easiest to read, and we'll see that going forward. So the big thing about stall pipe, it can be used to call arbitrary functions. We cannot anymore. We used to be able to create functions in user space and actually have this routine call them. We can't do that with iOS 6, but at least you can call arbitrary functions through it. In order to do that, you need to make sure that the object that you provide through the through the arguments there, you have to just make sure that it is observable from the kernel. So it has to be in kernel memory. And we also have to know the address to make it useful. And obviously we need to know the address of the function we want to use that information with. As I mentioned, I'm trying to speed up because I want to give David a lot of time. We can no longer access, the kernel can no longer access directly user land space, and whereas before it could. So we could literally just malloc a buffer in user land space, put whatever we wanted into it, dump functions into there, dump data into there, just pass it to stall pipe, and it would execute it or use that data. That lasted for a long time. That's been around for about 2 years, 2.5 years, since the first iPad 1. Nowadays, KSLR makes it challenging to first find the objects, and then of course modifying is a different story. And it makes it hard to know, now that we're limited to only calling what's already in the kernel, KSLR makes it hard to give it the right address to, even if you know what function you want to call, you need to know where it is, and that's more difficult. And again, create data creates this standard, Apple standard structure, an IO memory map, and it gives us its kernel address as the token, as I was talking about earlier. It lives, at the end of the day, it will live in one of the calloc zones. Because of the particular size of this element, it's always going to be in zone 88 decimal. Now if we call what we want to do, the purpose, what we're trying to do, it's not enough to know it exists inside that calloc zone. We need to know specifically where it's going to exist for a future call. And so what you do is you do a little bit of massaging. You call create data enough times to make sure that you're sort of in a nice clean page. You've sort of used up all the existing space in the current page for that zone size, and now you're somewhat into a brand new page. And as soon as you're far enough into that page, now you can sort of it's not a guarantee, but it's a very high probability that the next few calls will also be in that page and at increasing addresses from you that you can predict. And so once we are able to do that little bit of massaging to find the address that the next allocation will provide. So this is in reference to the whole idea about using this technique, to using these calloc zones for this purpose, came from Mark Dowd's paper and Tajay's paper a few months ago at Hack in the Box in Kuala Lumpur. And the whole goal here is to get data that we can control at a known location. So the basic process is you send these messages. You don't consume them right away. You send them a bunch of them in turn. They get interspersed in this pool. They get interspersed between the data, the header that encapsulates them, and our control data. Eventually, they will get flushed in a sense. They'll get used at some point. So you can't do this forever, but you can cause them to be flushed when you request the message at the end of the day. It's really interesting how it worked out. It only has it must fit in this 88 bytes. The header itself has 48 bytes, and so we can only use the 28 bytes hex, which is 40 bytes. 40 bytes ends up being 10 D words, and so this is too complex to go through right now, but you'll see right here we have 10 D words in this table, and this is the reference code. This is what I referred to. This was down in the corner before. This is ultimately what you're doing with this function, and if you go through it, and I'm not going to go through it now, this data up here that just fills that 40 bytes that you have can be used to give you a function that you can specify the function and you can specify one argument to that function. And David called that call indirect, and it's a sort of a primitive. It makes use of the IOUSP bug in a very specific way. We don't intend for a lot of the fields to do anything. We just need to make sure they're consistent and they pass the checks that are already in the kernel extension to treat it like a valid object to get far enough to do the call. And with that, I'm ready to go on to David's part. Fun being.
Thanks, Eric. So now we have sort of two of the pieces that we mentioned earlier. The first piece was to be able to get data into the kernel in the first place in order to create that fake pipe object structure. The second piece is to know the address of that object. And the create data call lets us fulfill those two requirements. The third thing is that now that we have a call indirect primitive, we need to figure out what function to call. The function must be kernel executable code, so it must be in kernel text naturally. And although we are able to leak addresses from the kernel heap, that doesn't help us know what code to call. And for that, we actually need to attack kernel ASLR head-on. So kernel address space layout randomization is a new iOS 6 feature. It shifts the start of the kernel by a randomized amount determined by the bootloader. And the entire kernel text is shifted as one block. So you just add a certain random number to every single kernel address. This means that if you know a particular landmark in a kernel, say a landmark of a particular function, say our stall pipe function, and you are able to retrieve the address of that stall pipe function for the current boot, then you can do a simple subtraction operation and get the KSR slide and be able to add that to every single offset and be able to know where everything in the kernel is. So is there a weakness to KSR? Well, when you look at it, the first thing that, maybe one of the first things that you'll see is that the exception vectors are not moved. These are ARM exception vectors. They're sort of, whenever something happens like an IRQ or a syscall, the ARM processor jumps to entries in that exception vector. And the ARM processor hardware on iOS devices, as far as I know, only have two options for the location of these vectors, either at 0x0 or 0xFFF0000. So that can't be moved. So the exception vectors in this case is always at that location. If that place was writable and you had a memory write anywhere gadget or primitive that did not require a KSR in the a KSR defeat in the first place, then you might be able to write to that location and then jump to it. But unfortunately, that location is like all addresses in kernel text. Every single executable page in kernel text is also marked not writable. It's all marked read-only. And also, another way you might be able to exploit it is you could maybe read it if you had a read primitive that somehow doesn't require KSR. Unfortunately, that does not work as well because the code there is position independent, and there's not really any useful gadgets in there. All it does is it takes this pointer to the real exception handlers from this thread ID CPU registers, which you can't access in userland, so you don't know where the actual addresses of anything are. It's just kind of a stub to call the real exception handlers. So to be able to use this weakness, it requires a little bit of creativity. And I discovered I discovered a way to exploit this weakness on accident. I was trying to read out the kernel. If you have the call indirect primitive, what that does is that it allows you to jump to an arbitrary kernel address after it dereferences a certain specified memory address into R1. So you can give it a memory address, it'll dereference that and put the result in R1. So it'll read the memory value of whatever you specify into R1, and it'll jump to whatever you specify. It's not very useful if you don't know where anything in memory is, But if you're able to do that, and if you're able to call, say, a random address that forces it to panic, then in the panic log, like every time there's a kernel panic, iOS writes this iOS panic log. You can read out all the kernel registers in this panic log. I mean, the system restarts, but you can use this way to read the kernel 32 bits at a time. So I was using that to investigate kernels that we have never dumped. We don't have any exploits for these new hardware, so we can only try to assume similarities between different kernels and try to get our bearings by reading 32 bits at a time. So I was trying to do that. But for some reason, when I was first trying to exploit the iPad mini and trying to get a dump of the kernel using this method, the kernel panic log was useless. It had some sort of CRC error, which was weird. And I sort of panicked. I was like, I did not know if there's any way to dump this kernel. So just out of desperation, I decided to jump to the ARM data abort handler just to see what would happen. Well, jumping to the ARM data abort handler did something weird. The system didn't panic, but the program that was running my exploit code crashed. So why? And in addition, the crash log for the program seemed to contain the kernel thread register state and not the userland thread register state for the thread when it was doing that stall pipe exploit. So why did this happen? Why did only the thread crash instead of the entire processor when we were doing something so crazy as to jump directly to the ARM data abort exception handler? And the answer is in how that data abort handler distinguishes between userland crashes and kernel mode crashes. So here's a little bit of background about the ARM architecture. There's a CPSR register in ARM that contains a bit field from the bit 0 to bit 3 that has it's called mode bits, and it basically tells the processor what mode it's in. There's a few different modes, user, FIQ, RRQ, etc. One of them is the abort mode, naturally. And when an exception happens, like a data abort exception happens, the CPSR state during the exception, like right before the exception, is saved in this banked register called SPSR. CPSR is the current program state register, and SPSR is the saved program state register, processor state register, I'm sorry. And then you can check, the exception handler can check the SPSR to determine what the previous, what the processor mode during the exception was. The instructions, there's a bit of complexity in that there's the SPSR register is banked, so there's a different copy of the SPSR for every single processor mode. But the instructions to access any of the SPSR registers are the same. It's just the instruction to access the SPSR register in the current processor mode. So basically, if you jump directly to the data abort handler without actually triggering a real data abort exception, the SPSR is going to be is not going to reflect when you jump to the data abort handler. Instead, it's going to reflect when you first enter the syscall. I guess I'm jumping ahead a little bit, but the code for the data abort handler, it tries to check what the processor mode was during the exception. So it would read this little, I don't know if I forget the laser pointer, but it reads SPSR into SP, and then it checks the bits 0 to 4 of the SPSR of SPSR. And if mode is 0, then the old CPSR, the old processor mode during the exception was user mode. And well, okay, thanks. And so you will handle that as a user mode crash, as in just crash the current thread. But if the mode is not 0, then you know that the processor state during the exception was kernel mode, in which case something seriously wrong has happened, obviously, and you should just panic the entire system. So as I was saying earlier, if you jump to the data abort directly instead of actually crashing, it's not a real crash, you're just jumping to the data abort handler, then the SPSR that the data abort handler will read is actually what the SPSR was when the syscall that triggered stall pipe eventually was, in which case it was user land. So the data abort handler therefore thinks that there was a crash in user land at that point. And then it doesn't retrieve the user land registers. It just dumps the saved processor state, the kernel registers. So basically, if you just call the data abort handler, that just turns that data abort handler into a function to dump the current kernel registers, including PC. So this is a pretty powerful info leak, because not only does it leak PC, which allows you to calculate the kernel's ASLR slide, it also lets you leak a 132-bit integer, because if you use call indirect. So what we did in Invasion is we registered a thread exception handler for this thread that we deliberately use call indirect to call into the data abort handler. And this way, we're able to leak information. So we crashed the thread kernel from stall pipe, and then we were able to get this address, the current address stall pipe 1, and then doing simple subtraction on what the offset is at, we know what the KSR slide is. And then we can also use that to just leak any arbitrary kernel memory. And using that, we can leverage eventually finding gadgets and eventually dumping the whole kernel. And then we can use the patch finding code, the offset finding code, to generically generate a set of offsets and gadgets that we can use on the device. And the special thing about Evasion is that with this powerful info leak exploit, we didn't have to hand calculate any of the offsets or the gadgets. It's all very generic code. As long as these vulnerabilities exist on a system, we're able to exploit them without knowing anything else about the system. So I thought that was really cool. So obviously this is very useful because there's 5 different varieties of iPads, and we're supporting maybe 4 different firmware versions. So the possibilities are the different permutations of kernels is just too many to handle by hand. There's a bunch of slides here that talk about details of this process, but I think we're probably out of time. So maybe we should just skip straight to questions. Do you guys think that's a good idea? I mean, there's a lot more details. One of the caveats of this process is that well, let's just go to questions. If there's no questions, I can go on for a while.
Hi, excellent research, really awesome. Things are getting harder and harder. Will this be the last jailbreak?
Well, I mean, I don't think so. I think there's probably still, I think there's definitely exploits that haven't been discovered, and I think jailbreaks will continue for some time. Does anyone have a better answer?
This USB one, like I said, has been around for 2 or 3 years. So we were using it internally. It turned out for different reasons not to be widely deployable, but because we didn't use it, we didn't call it to Apple's attention, and it was usable two years later for this very widely distributed jailbreak. So there's lots of that still left.
Yeah, maybe. Good news. Thank you.
David, would you like to continue further with the caveat?
Yeah, sure. We can talk a little bit about some details of this thing. Unfortunately for this method of the exception handler, due to how IO Connect call works, it always leaks 6,144 bits every time you do it. So you can't do it too much. You have to use it to leverage finding better primitives, gadgets for better primitives later on. The reason is because there is the system, the IO kit call is actually a mock message, MIG call, and that eventually calls this function called IPCK object server in the kernel, and that allocates a reply, an error reply, just in case the function errors out. And unfortunately, this reply is allocated on the kalloc heap, and the value of the pointer is stored on the stack. But before we can properly return and unwind the stack, we call the data abort handler, and that exits kernel mode through a function called thread exception returns, and that doesn't unwind the stack normally. So that current kernel stack is lost forever. So.
And this really, really bugged David.
This really bugged me, and I really like writing clean code, and technically we only needed to have one of these fake crashes per boot, so you lose 6 kilobytes out of 256 or 512 megabytes, and maybe that's not a big deal, but I'm completely OCD, and I wanted to, so I manually searched every single page in memory that belonged to the kalloc pools to find that missing object and free it properly.
And you spent like 2.5 days,
well,
like 20 hours a day.
2.5 days. But it was good enough.
You emerged after days of battling this monster.
Oh, it was fun. So,
yeah.
And then in the another slides we had there are some other primitives that we can create with those function call primitives. We can find a gadget that allows us to basically write anywhere. It's just a very simple gadget that takes the value of R1 and stores it to the address pointed to by R2 and then returns right away. And that lets us, if we call that, it basically lets us write cleanly to any address we specify. And this is a read anywhere primitive that does not use the crashes, but it does require knowing where memmove is. What it does is that the first argument when you do call indirect, the first argument to that function that you can arbitrarily call is only semi-controlled. It points to the middle of one of the OL descriptor buffers. And because of that, if you call memmove, the destination argument will therefore be in one of those descriptor buffers that you are passing in. So you can specify the second argument to be where you want to read from, and the third argument to be how much you want to read. And as long as you keep the read small enough to fit into that 40-byte buffer, then less 5 times 4, less 20 bytes. So if it's more than 20 or 24 bytes, then you're able to use this method to read 20 or 24 bytes at a time.
Now, in a sense, this is overkill for jailbreak purposes. It's it's overkill for jailbreak purposes. It is the kind of thing that would be useful to a black hat attacker who doesn't have a lot of other requirements that we do. You use this to do kernel dumps and such like that, but it's not useful overall. It's not useful per boot, and it's useful for exploration. And it's a lot of work to get to this level of a primitive.
Well, yeah. I could have hard-coded a lot of values. One thing that we do use this for is, I guess this is also important to say, is that eventually we want to get to a point where we can patch the kernel. Now, Apple has set is another one of iOS 6's security improvements is that finally now kernel code that is text pages that are executable are no longer writable. So that's great. But you can still, the actual hardware page tables that those permissions are based on are still writable, obviously, they have to be. So you can change the page tables. You can use your write anywhere primitive to alter the page tables to make the rest of the executable pages writable. And in order to traverse the page tables, because sometimes you have to go into randomly located second level page tables if you don't want to brute force it, you do ideally need to read memory to be able to know where the page tables are and what their current state is, so you can cleanly modify them. and there's another larger read anywhere primitive that we use that was also based on Mark and Tarjay's work. Basically, we use the memmove trick to corrupt the VMMap copy header structure. One of the ones that we pass in the OL descriptors. So when we receive the message, after we have corrupted one of those headers, it will let us read arbitrarily anywhere in memory. So you can see their presentation on details about that method. So the slides basically show details of my implementation of this method, but it's rather complex, and I have a hard time explaining it anyways. So. Yeah. So basically, like one of the things about this jailbreak that I hope will contribute to the future of jailbreaks is that now we have a nice set of patch finding routines that can automatically find offsets. Like the family of iOS devices has grown so much that no one wants to manually go through, look at every single kernel variation or userland software variation and find all the offsets. So if we have that, then it will be much easier to create jailbreaks that work on all devices. Another thing is that we have a pretty stable GUI that we've developed over the month using Corona and Rocky Raccoon, and now we're able to have it be internationalized. So we can serve a large growing population of non-English speaking jailbreak people. So that's basically all we have.